Okay, so this is a suspension solver made in Python. Um, right now, it's purely kinematic, and it's only doing it for one side of suspension, I guess. So here, you can move this around. You can see the coordinates, and you have the UCA, LCA, the upright assembly, and the push rod and rocker. And over here, you can select just like how you can in Optimum K, you can select heave, pitch, and roll, and how the range of heave, pitch, and roll. And then I also have a slider here, so you can slide it and watch it move, which I think is kind of cool, which Optimum K does not do. And then on the side, just like Optimum K, I have all of the coordinates for all of the suspension points. And you can go in here and change any of them. And then on the bottom, I have the graphs. So for heave right now, I got the camber graph. So you can see for 50 millimeters of heave, it's like zero 0.1 camber degrees. It's not representing the actual FSA car. It's just a random setup. And I've got the roll center height, the toe, and the motion ratio. I think it's pretty cool, and well, my goals with this in the future is to have the full car set up in Python that you can run locally on your computer. And then from there, once I have the full kinematics figured out, I want to move on to inverse kinematics. That is, I give it the curve, for example, camber, and then it's going to solve for the coordinates instead of me entering the coordinates and solving for the camber curve, which is going to make our lives a lot easier. And after that, I want to move on to dynamics and see how the actual point masses on the suspension and the center of gravity will affect the suspension when it's accelerating and braking, so we can have a more in-depth simulation of how the suspension would work in real life. A little bit about how all of this works. So the way the points or the lengths are defined is we have 12 unknowns and 12 knowns. So the 12 knowns are the inboard points, which are over here, and then the 12 unknowns are over here. And the lengths are defined by this square roots, no, sorry, the roots, the squares, sorry, the squares. And then it uses a Newton-Raphson method to figure out when you move this 50 millimeters high, and then you make a guess. Let's say the length of my linkage is 300 millimeters, and your guess is 312, and then you take the difference of the squares of it, and then you get like a residual of say 14,000, right? And then you know that, well, I have a big residual, it's wrong, I need to make another guess. But how do you know in which direction you should make the guess? Should you make the guess bigger, so 324, or make the guess smaller, like 310? Well, the answer is to make it smaller, right? Because the length of the link is 300. So for that, it's using a Jacobian matrix. So it's a matrix of 12 unknowns and 12 knowns, and it does funky math, and it figures out in which direction you have to make that guess. And then it makes that guess again until the residual is smaller than 1 times 10 to the negative 5. So it's a pretty small number, and it's going to keep iterating until it makes that guess. And I think for how accurate it is, it runs pretty smoothly, and I'm excited to see what I can do with this more.